In this lecture, we are going to look at what happens to solar radiation, shortwave radiation, or insolation that gets to the Earth's atmosphere, what it does and how it does its heating as well. As solar energy or insolation passes into the Earth's atmosphere, not all of it reaches the ground. Some of it is scattered by oxygen in particular in the atmosphere. A large portion of it is reflected away from the Earth. That's referred to as the Earth's albedo. It's particularly strong in areas that are cloudy because clouds are, of course, white, or also ice areas which are white. Some percentage of it, though, is absorbed directly into the atmosphere, and some of it is also absorbed by the ground as well. Once that energy is absorbed by the ground, the Earth begins to heat, and it begins to put off more thermal radiation than it had before. That thermal radiation, in turn, plays a very big role in, again, heating the atmosphere through what is sometimes known as the greenhouse effect. The greenhouse effect refers to the fact that certain gases in the atmosphere, particularly water vapor and carbon dioxide, but a range of other gases as well, are very efficient at absorbing infrared radiation. So the energy heats both directly from solar energy and indirectly from thermal radiation, and that principle is very important. Clouds play a big role not only by reflecting light away from the planet through albedo, but also by trapping it inside the atmosphere, causing reflection and counter-reflection of infrared radiation within the atmosphere. You've probably noticed before that cloudy nights are often much warmer than those that have no clouds, and that's because of that insulating role that clouds can play. Another important point to note before we go on, as we've already stated, is that the equatorial areas have much more energy coming to them than the more polar areas do. Let's look at a couple diagrams. This is a diagram you should take a look at. Again, you don't have to memorize the numbers here, but you should appreciate the fact that of the energy that comes from the sun, which is 100%, about 31% of it never makes it to the planet. About 18% of it is absorbed by atmospheric gases and dust. 25% of it, and another 20% that's diffusely absorbed, is absorbed by the planet itself. That energy from the surface of the Earth plays a really big role in the heating of the atmosphere. So when we start thinking about how the atmosphere heats, we shouldn't just be focused on the sun, but also the role that the Earth is playing as well. And of course, that heating is going to be most effective in the equatorial areas where we have a much greater amount of energy coming in every day, every month, every year, every 100 years, whatever, than we have going out. Polar areas are in an energy deficit, and that will play a really big role later as we start to think about how the atmosphere circulates and how heat moves in the atmosphere. On a daily basis, it's very important to understand the relationship between infrared radiation and solar radiation because daily temperatures are impacted by it. Insolation is being absorbed throughout the day as the sun shines on the planet. It's also heating the atmosphere as well. But as I've already stated, it's the infrared radiation that comes from the surface of the Earth that does an even more effective job of heating the atmosphere. So objects on the ground are absorbing insolation all day long. They're at their peak at noon, or whenever the sun is highest, which is the real noon. But it's still very effective heating taking place just after noon as well. And because the energy that comes from that absorption is what is so good through infrared radiation at heating the atmosphere, we tend to see a time lag between when the sun is at its highest and when the warmest time of the day is. In fact, the warmest time of the day is sometimes after noon, 1 p.m., 2 p.m., 3 p.m. A lot of it is affected by what time zone you're in. A lot of it is affected by whether or not you're close to an ocean or whether you're in a big continent, a bunch of things that we'll talk about later on. Once the energy from the sun drops off and it ultimately sets, there's still energy that has been stored in the planet that continues to heat the atmosphere, which is why air temperatures are still warmer in the middle of the night and don't become their very coldest until right after the sun rises, which is the coldest time of the day. So there's a time lag pattern. Now, of course, that time lag pattern is often very strongly influenced by weather events. So if a storm moves in the middle of the night, temperatures might actually increase at night rather than decrease. But if you look at averages over many, many days, long period of time, you'll see that it is always going to be coolest on average right before the sun rises. So a friend of mine, Brian Brettschneider, who is a climatologist for the National Weather Service, created this graph for me years ago. It's the temperature at different times of the day throughout all of 2008. And what we can see is that the coolest time of the day on average in Anchorage in 2008, but any other year as well, because these averages will be very similar to one another, is somewhere around 5:30 in the morning. The warmest time of the day is in the afternoon between 3 and 3:30. And even though the middle of the night at midnight is the darkest time of the year, the temperatures are still falling because energy is still being lost from objects that were warmed on the ground. These sorts of things happen seasonally as well. The warmest time of the year is not when the sun is at its highest, which is the summer solstice, but actually a little bit after that, because there's still a lot of good heating taking place after June 21st. And in fact, in Anchorage, this is a temperature graph for all of Anchorage over many, many years of data. You can see that the warmest day is July 20th. It's usually somewhere between July 16th and 30th. Those dates are all very similar to one another, with a high of either 66, this one says 68. It's based on where the temperature data is coming from and how that's being counted, with a low for that day of 53, or an average temperature of 60 degrees. The coldest days of the year tend to be between January 6th and January 28th, where we have a high of 23 and a low of 11, or as this graph shows, a low of 13, with an average of 17. Again, this doesn't take place at the darkest time of the year, which is over here in December, but instead a little bit after that, because the quality of light that's coming to Anchorage between December 21st and late January is still quite poor, and things aren't heating particularly well. This is all a reflection of the fact that solar energy heats the Earth, but the Earth itself is what's so good at heating the atmosphere. A couple of other things can really impact temperature profiles as well. Obviously, this includes latitude. The farther north you are, the cooler the temperatures are in general. The farther south you are, or closer to the equator, for the northern hemisphere that is, the warmer things are. But altitude can play some role as well, especially when we start to be up in very high mountainous areas where temperatures are generally cooler because we just don't have as much atmosphere to heat. And cloud cover can impact temperature as well. For physical geography assignment number 2, these are all things that you're going to need to think about. Another big thing that plays a role in temperature variations is whether or not you are close to big bodies of water or you're right in the middle of the land, producing something that's called continental versus maritime effects. Water evaporates energy, causing cooling, Water's transparent, so you have to heat a large mass of it before you get it really warm. It's a little bit harder to heat water as well, and it moves energy around. And as a result of all these things, maritime areas, or places close to water, tend to have much cooler summers and much warmer winter times, whereas continental areas are just the opposite. So here are some examples. Utqiagvik has cold temperatures, as we would expect, much colder than what we find at other latitudes. It's a little bit of a more continental climate, even though it's right by the Arctic Ocean, but the Arctic Ocean is often frozen with ice. And as a result of that, the temperatures are pretty profoundly different between the summertime and the wintertime. Compare that to Edinburgh in Scotland, where we have a much flatter temperature profile. Obviously, it's at a lower latitude than Utqiagvik is, and as a result of that, it's a warmer place, but its winter times are relatively warm, and its summer times are relatively cool because it's so close to a body of water, unlike Montreal in Quebec, which is at a latitude of 45, so actually even further south than Edinburgh, but it's a much more continental climate, so much bigger swings in temperature between the summer months, June and July right here, and the winter months here. Some places, especially equatorial areas, have very little temperature fluctuation whatsoever. Not only do these tend to be maritime areas, but they're also areas that are always getting really good quality light. Here's a couple of other examples. From the textbook right here are two places that are both located at about the same latitude north. I think it's somewhere around 37 degrees north of the equator. Here is San Francisco, and this is Wichita, Kansas. San Francisco, of course, is right by the Pacific Ocean, and in fact, a lot of the winds prevail from the Pacific over San Francisco. So we have very little temperature fluctuation, even though the latitudes of these places are the same. So the latitudinal variation and the amount of daylight that they get at different times of the year is exactly the same. Wichita, being right in the middle of the continent, doesn't have that moderating effect of the ocean, and so its temperatures get much warmer in the summer months and much cooler in the winter months, as we would expect. Another cool thing to see about this is that in San Francisco, the warmest month is actually September, way after the sun's maximum, because the ocean is storing so much energy and releasing it slowly. I made a little graph right here that compares Anchorage to Fairbanks. Now, it's not a perfect comparison because they're at different latitudes, but Anchorage is a little bit more maritime, so its temperatures are more moderate. Fairbanks, on the other hand, is a little bit more continental. And then the last couple of maps to show you right here. This is a map right here that shows the average temperature for every part of the planet in January, and another one for July over here. And what you'll notice looking at this is that the big continental areas like Eurasia and North America have much bigger swings than the more maritime southern areas like South America, Southern Africa, and Australia. In fact, this next map right here does a comparison between them and essentially subtracts the highest temperature from the lowest temperature to produce an annual temperature range. And you can see that central and northern Canada and Siberia are the places that have the biggest temperature fluctuations, whereas equatorial areas have almost no fluctuation. And even relatively far to the south in the southern hemisphere, there's little difference between summer and winter time because there is such a maritime effect in these areas. These are all things to think about and things that you are going to put into practice as you work on physical geography assignment number 2.